Welcome to EC342 Optical Link Project, Task 2 Briefing, Active Bandpass Filters module. Let's start with the function of this active bandpass filter in the Optical Link project. The second stage in the receiver, which comes after the first stage, the transimpedance amplifier, will amplify the signal while limiting the effect of noise on the received signal. This is accomplished by using a narrow bandwidth filter. The 3 dB bandwidth of this bandpass filter should be large enough to accommodate the plus and minus 5% tolerance of the clock frequency. And we will accomplish this by using one or more stages of the multiple feedback bandpass filter. First of all, let's start with the concept of noise. Where does this noise come from? Electronic noise comes in two flavors. The first is due to the random fluctuations in voltage and current due to the quantum mechanical, that is statistical nature of electronic devices. These actually include resistors, capacitors, and inductors as well as transistors, diodes, and so on. The other type of noise is, of course, interfering signals. Other signals that exist in the media all around us, right? You have your Bluetooth, your Wi-Fi, cell phones, television, FM radio, AM radio, satellite TV, and so on. To reduce interfering signals, we use a highly selective bandpass filter, a very narrow bandwidth filter. It turns out that this will also reduce the other type of noise, the electronic component noise as well. So what are the types of electronic noise that we can find in order of appearance in our receiver chain? The first is the photodetector noise. The photodetector, essentially the primary noise there is shot noise. The photodetector also suffers from other types of noise that are going to be noted below for transistors, but the primary mechanism for noise in the photodetector will be the shot noise. Resistors suffer from thermal noise, also known as Johnson noise. As far as the transistors and op-amps, after all, op-amps are transistor circuits, there's several types of noise associated with them. There's shot noise, which is due to the carrier injection through a PN junction. There's the generation recombination noise, which is due to the statistical nature of the generation and recombination of carriers in semiconductors. We have 1/F noise, which is usually associated with material failure and imperfections in fabrication. 1/F squared noise, which is usually associated with metal semiconductor contacts. For a relatively straightforward description of noise types in semiconductor devices, you can follow the link below. This link is also repeated at the end of this presentation. So which of these noise sources limit the receiver? In a well-designed receiver, whether it's an optical system, an RF wireless system, cable wired system, the first stage should set the noise floor. You will encounter a not well-designed system in Task 5, and we'll figure out how to fix that in Task 5. Every following amplifier stage after the first stage will add its own noise in addition to amplifying the signal and the noise from the previous stage. So while the signal is getting amplified, noise is not just getting amplified, but it's getting added too. So it's getting amplified at a much faster rate. So the signal-to-noise ratio is getting worse as we go up the amplifier chain. That's not good. So the first stage, the transimpedance amplifier in our system, should have the smallest possible noise figure. And in order to achieve this and to figure out how to limit the effect of noise on the receiver, we need to understand what this shot noise in the photodetector and the thermal noise in the resistor is. Let's start with the shot noise in the photodiode. This is given by the square root of 2 times electron charge Q times the dark current times delta F, the measurement frequency bandwidth. The dark current is the current of the photodiode with no light incident on the device. Essentially, if I take a photodiode, reverse bias it with, say, 5 volts, and I cover it up, that's the current that I would measure for that particular bias voltage. In our case, we're using the photodiode with a transimpedance amplifier, and there's essentially no bias across the diode the way we've connected it. So I dark should be 0. However, the photodiode is also going to detect the background light, which will generate a photocurrent that will behave like the dark current, because it's not related to the signal that we are transmitting. So we will take this photocurrent and treat it as if it's the dark current. So if you build an optical link in the future, for example, you're building a fiber optics communication system, a LiDAR receiver, or something like that, use optics to limit your noise signal. Use lenses to properly focus the light, use optical filters. You can find them with, say, 10 nanometer bandwidths to limit the optical bandwidth and hence the noise that will come through. In our particular case, we're not using any optical components at all, but that measurement bandwidth delta F is the other limiting factor that we need to worry about. And luckily for us, that is something that we can determine. That delta F essentially is going to be the 3 dB bandwidth of the bandpass filter following the transimpedance amplifier. So if you use a high quality factor that is narrow bandwidth active filter, we will limit the noise. What about the thermal noise of the feedback resistor in the transimpedance amplifier? Well, thermal noise is essentially due to the random motion of atoms and electrons in the resistor that is caused by thermal energy. At 0 Kelvin, nothing has kinetic energy. Above 0 Kelvin, everything in the universe has kinetic energy, which means everything is moving, including the atoms that make up our bodies and furniture and so on. So, the thermal noise, also known as the Johnson noise of a resistor, is given by the following equation: 4 kT delta F over R. K subscript B is the Boltzmann constant, T is temperature. KT essentially is thermal energy. Delta F when we look at this, we see that the equation is inversely proportional to the square root of R. So the noise current is inversely proportional to the square root of R. If we make the feedback resistor larger, the noise will get smaller. So we should make RF as large as possible. This not only means we get good gain, it also means we actually limit the noise. That's beneficial. And it makes sense that this noise current is inversely proportional to the resistance value. The larger the resistor, the smaller the effect of that, incremental motion of the atoms within their location. After all, they're not going to move any more than an angstrom or 2. The noise current for the resistor, the thermal noise, is also proportional to the square root of delta F. So this tells us that we definitely need to limit the measurement bandwidth. Now that we have an idea of what the noise sources are, we should figure out what our link budget is. This is the power budget. Any communication system that includes radar and LiDAR systems has a link budget. This is in terms of the available power, not the dollar cost of the system. And trust me, the dollar cost is going to be exponentially dependent upon the power budget. We need to figure out how much power that we are going to transmit, how this power drops with distance, and then we can figure out how much signal is available. Now, those of you who took EC 351 should have hopefully seen the Friis transmission formula. Now, that formula was developed for an antenna system, an RF system with a transmitting and a receiving antenna, but it turns out that it works for our photodiode and LED optical link as well. What the Friis tower will tell us is that the power will drop with 1 over R squared. The power density will drop by a factor of 100 for an increase in distance of 10. So we can determine the required gain at the receiver to obtain the desired signal levels based upon this calculation. Here's a plot of the power density versus transmission distance for the infrared LED that we are using. The LED output power is 8.4 milliwatts, and I determined this from experimental conditions using my Ocean Optics red tide spectrometer and integrating sphere. Yes, I do trust the data sheet, but I also prefer to verify their data. So you can see that the optical power density drops quite a bit. In fact, at 50 feet, it's almost 6 orders of magnitude less. Sorry, at 50 meters, it's almost 6 orders of magnitude less. Now that we have an idea of how much power is available, we can determine the limit of detection for the optical link. This is essentially set by the noise floor of the receiver. We need to calculate the signal current and compare it to the noise current. We can calculate the signal current based upon the OP999 photodiode sensitivity, or responsivity, in other words, the signal frequency of 20 kilohertz. This is essentially large enough to avoid the 1 over f and 1 over f square noises, so we can simplify the noise calculations. The signal bandwidth of 2 kilohertz, the plus and minus 5% tolerance for the clock frequency, a TCA gain of 39 kiloohms, which is less than your limit due to the compensation capacitor size. You should be using a larger TCA gain, and an optical power density versus distance given in the previous slide. My assumption is that the background current is 10 nanoamps for the photodiode. That's actually pretty large, so we're being a bit pessimistic with this calculation. And the result is in this blue graph. The blue line is the photodiode current, the photocurrent, whereas the dashed red line is the noise current coming from the photodiode and the TCA's feedback resistor. The noise current would essentially be about 30 picoamps for a feedback resistor value of 39 kiloohms. If you used 82 kiloohms, then that would be about 21 picoamps. But when I look at this graph, that tells me that the photocurrent should be at least 20 decibels above the noise floor, even at a distance of 50 meters or 165 feet for a well-designed system. Now keep in mind, this figure only accounts for the receiver's 3 dB bandwidth, nothing about the receiver gain. How are we going to calculate the gain? The photodiode current should be about 1.7 nanoamps at 50 feet, if the LED and the photodiode are aligned and working as specified. So that means that the TCA output is going to be less than 170 microvolt RMS at 50 feet. You need a 5 volt digital signal at the output, or as close to it as possible. Well, here's a caveat. This is the ideal case if we were building a real link. On the other hand, in this project you are held to a specification of a 6 decibel signal to noise ratio at 50 feet, as calculated by the digital and spectrum analyzer. That software actually uses built-in DSP filters to filter out the signal, so you'll be doing a lot better with much smaller signal amplitudes than 5 volts. Anyway, assuming that we are going to restore the signal to a 5 volt peak square wave, the overall voltage gain of the receiver stages following the transimpedance amplifier need to be about 83 decibels, so well over 10,000 volts per volt. These stages also need to limit the 3 dB bandwidth to improve the signal to noise ratio. Ideally, the 3 decibel bandwidth should be 0. You should be amplifying just the signal and nothing else. On the other hand, you need at least a 2 kilohertz 3 dB bandwidth to account for the clock frequency tolerance. A caveat is, after you build your clock circuit, your transmitter circuit, you might be able to tighten up your 3 dB specs for your receiver to improve your transmission distance. We're going to use the multiple feedback bandpass filter topology. This is a filter, an active filter, which means that it amplifies the signal while bandpass filtering it. The gain K and the quality factor Q of this filter are related to each other. They cannot be set independently. If you have a high gain, you'll have a high quality factor and therefore a narrow 3 dB frequency. If you don't know this already, the quality factor of a bandpass filter is defined as the center frequency divided by the 3 dB bandwidth of the filter. The design equations for the MFBF are given in the lab manual, in the MT220 mini tutorial from Analog Devices, as well as my handwritten notes posted on Blackboard. So you have plenty of information to base your design on. How will you go about this design? In the active filter stage, you need to achieve at least 1000 volts per volt or larger gain at 20 kilohertz. We will use an additional amplifier at the end with a gain of more than 10 volts per volt, so you don't need to get 10,000 volts per volt with the active filter. Now here are two questions to answer. Can this be done with a single op-amp? If you had a single ideal op-amp, would you be able to achieve this with the 2 kilohertz spec, the 2 kilohertz 3 dB bandwidth spec? And furthermore, since you have an LF347 practical op-amp, can that handle this gain at that frequency? When you do your design, choose the two capacitor values to be equal for convenience. Then you can calculate C1, R1, and R2 from the design equations. The caveat here is to make sure that R1 is larger than or at least equal to 1 kilo ohms to avoid problems with the op-amp's output resistance and current drive capability. If you go back to the datasheet, you'll see that the op-amp will have an output resistance on the order of tens of ohms, and it won't be able to drive a resistance less than 1 kilo ohm, a load resistance less than 1 kilo ohm. So the preceding transimpedance amplifier would like to see an R1 that is larger than 1K. Here are my experimental results. I'm just providing you the gain magnitude versus frequency scan from 1 kilohertz to 200 kilohertz. And here's a close-up of that showing you what happened in the 3 dB bandwidth. My peak gain is close to 69 dB, but it's a little off. It's not exactly 20 kilohertz, which you would expect from not having ideal component values. And the 3 decibel bandwidth is about 1960 hertz. So just about that 10% requirement. I have provided you with a pretty detailed step-by-step test and measurement guide, an MFBF test case document on Blackboard. This is similar to documents that you would find for acceptance testing, quality assurance testing, and so on at a real company, or at a company for a real project. So follow the steps on that guide. They are more detailed than you would find under normal circumstances. This is just an introduction to this type of procedure. And also read the 2 test notes at the end to understand some of the problems you may, and indeed will, encounter. So how are you going to go about measuring the gain of the MFBF? The first thing to note is that the Digilant has a 500 microvolt resolution limit. This is true for both the DAC, the digital to analog converter, for the waveform generator output, and the analog to digital converter, the ADC, at the oscilloscope channel input. So essentially, any signal with a peak magnitude less than 2 millivolts is going to be interpreted as a square wave. And any signal less than 5 millivolt peak is going to be too distorted to analyze accurately with the Digilant. So you need larger signal than those values. To do this for the input side, so with the AWG side, I would use a 100 to 1 or 1000 to 1 voltage divider to make the input small, and I'd use a large input signal. Ideally, you would like to use 100 ohm to 1 ohm, but the Digilant AWG can't drive it so well. So just make sure that your voltage divider total resistance is more than 500 ohms, and then you can use a 100 millivolt or 1 volt amplitude signal for your testing. Make sure that you measure the voltage divider's insertion loss and then factor it in to your final gain calculation. To do this, connect the wave generator output, the waveform generator output AWG1 and the oscilloscope channel 1 to the divider's input, and connect the channel 2 oscilloscope channel 2 to the divider's output. To measure the active filter's gain, do the measurement from the voltage divider input to the output of your amplifier, then factor in the voltage divider afterwards. So connect the channel 1 oscilloscope and the AWG1 output to the voltage divider's input, and connect oscilloscope channel 2 to the active filter's output. To make life easier for yourself and to make your data a bit more accurate, partition the measurement into 3 frequency ranges. If you assume a 1000 to 1 voltage divider, as I used, you could use 1 kHz to 10 kHz and 30 kHz to 200 kHz for the low gain regions, and 10 kHz to 300 kHz, 10 kHz to 30 kHz for the high gain region. This will impact what you set your max gain parameter to in the network analyzer mode. For the low gain regions, you can use 0.1x or 0.01x. This essentially adjusts the filter parameters in the Digilent's own processing software, and it will help you make more accurate measurements. For the high gain region, set the max gain to about 20x. In my case, since I used a 1000 to 1 voltage divider and my overall gain was about 70 dB, the apparent gain measured by the network analyzer was 70 minus 60, 10 dB. Export each measurement as a .csv file, stitch it in Excel, MATLAB, etc. to give you your full data set for processing. If you want to be really accurate, you should do multiple measurements because there's going to be noise present in each measurement. What I did was do each measurement at least 3 times and then average them to get my measured value. I can also, by the way, present my error bounds, which is what you would typically do in a real situation. You don't just do a single measurement and present that to your customer. You do multiple measurements over multiple devices, and you present your mean value as well as your deviation to give them confidence that your product works as advertised. So here are some tips and tricks for this lab. If you use 2 or more multiple feedback bandpass filter stages, do their center frequencies need to be identical? Check out figure 17.49 and its associated text in the textbook to see what I mean. Follow the procedure outlined in the document amplifier characterization.pdf on Blackboard. This will make life easier on you. It will make troubleshooting a lot easier. Use the scope and the waveform generator to make sure that the input signal is small enough so that the output isn't clipping and the output offset isn't causing the amplifier to rail. Once you've done with your transient measurements, then you can use the network analyzer mode to measure gain as a function of frequency. Something to watch out for is the Digilent's power rails and AWG outputs are very, very noisy. You might be surprised to just connect your AWG directly to the filter input, and even without turning it on, you have a huge rail-to-rail output at your output. Well, that's because the AWG can have a pretty large noise on the order of several millivolts, and if you're amplifying that by 1000 volts per volt or more, you get a pretty large signal at the output. If you use the voltage divider, especially a 1000 to 1 voltage divider, you'll be able to attenuate that noise and make your measurements a lot nicer. The other point to watch out for is the power supply rejection. You're probably used to treating the wires that you use in the breadboard connectors as 0 ohm ideal connections. Well, they're not. They have maybe 0.1 ohm, 0.2 ohm, 0.5 ohm resistances. The current draw from your signal due to your signal variation can cause ripples on the order of 1 to 10 microvolts. If you look at the supply current that the LF347 draws, that's about 7 milliamps. 7 milliamps and a 0.1 ohm resistance means a 700 microvolt drop through your wire, voltage drop through your wire. Well, when you first turn on the power supply, there's going to be an infinite number of frequency components in that step function. The LF347's power supply rejection ratio at 20 kHz is only 40 decibels, and you're building an amplifier with a gain of more than 60 decibels. So that means that the ripple will be amplified by at least 20 decibels, if not more. In my case, it was actually 30 decibels. This will pull in more current, causing further ripples, causing more current draw, and so on, essentially causing an oscillation. It's one of Murphy's design rules. If you want to make an oscillator, design a high gain amplifier. you will probably see your amplifier acting as a beautiful oscillator, perfectly oscillating at 20 kilohertz with a very close to sinusoidal waveform. To avoid this, if you run into this problem, you will need to use bypass capacitors at both supply pins to eliminate oscillation, as Dwayne Hanselman discussed in EC210. Here are some references for you on electronic noise. I will post this as a PDF file, so you'll be able to follow these links.